In section 3.1, we go over a couple of different types of functions that we study in this chapter, the exponential and logistic function. We'll look at how do we identify these functions, how do we graph them, and then kind of most specifically we'll work into the end of the lesson, how can we work problems that are modeled with these types of functions. Well, let's begin by defining an exponential function. We define an exponential function this way. We let a and b be real numbered constants, with a being non-zero and b being positive and not equal to 1. The function f of x equals a times b raised to the x is the exponential function, where a is called the initial value and b is called the base. So some vocabulary here to know. Most notably, you see kind of different about this function than maybe some polynomial functions we've seen in the past, because the polynomial functions do involve exponents, but here the role of the independent variable x has been flipped from the polynomial functions we've seen in previous chapters, where here the x, the independent variable, is the exponent instead of being the base as we've seen in the past. Okay, here we're asked to determine if the function we're looking at is an exponential function, and if it is, identify its initial value and its base. So just getting comfortable with an exponential function, being able to recognize it is kind of the idea here. This first one, yes, it is exponential. I could say my initial value, I'm just going to use a, is -3, and my base b is 4. Okay. The second one, I would also say yes, it is exponential. Here the initial value, and this is kind of the tricky part maybe, the initial value is hidden. It's really there. The initial value a is 1, the base is 5. Okay, so that could be that particular function could be thought of as 1 times 5 raised to the x. So there is our initial value in there. The next one looks a little different. You notice that the exponent is negative, but yes, this is exponential. So let's break it down. The initial value a is equal to 7, and the base b is equal to 1/2. Okay, why 1/2? Well, if we look at this part, this 2 raised to the negative x is the same as 2 raised to the -1 raised to the x. If I just pull apart that negative x as the product of -1 times x, and of course 2 raised to the -1 is 1/2. This last one, I would say no, not exponential. It's not exponential because the exponent is constant. This right here should be x, and it's not an x. So that's why it's not an exponential function. Next, I want to go over the graph of an exponential function. So what I did is just picked 2 raised to the x. I just tried to pick a simple exponential function where we kind of keep the numbers as simple to work with and maybe as small to work with as possible. We're not going to be doing a lot of graphing of exponential functions in this particular lesson, in this particular class, but I want to go over this so we can kind of see the general shape and form of these exponential functions and maybe think about their domain and range that they may have. So with this exponential function, let's just begin by making a table of values. And maybe I'll start with 0. So I would plug that in, and 2 raised to the 0 power is 1. That should kind of make sense to us because this function really could be thought of as 1 times 2 raised to the x, and the 1 is the initial value. So that should be the starting value, which is right there where x equals 0, right there on the y-axis. That should be 1. When x is 1, 2 to the first power is 2. When x is 2, 2 to the second power is 4. When x is 3, 2 to the third power is 8. When x is 4, 2 to the fourth power is 16, so we're off the graph now. So if we look at some negative values, if x is negative 1, 2 to the negative 1 is 1/2. If x is negative 2, 2 to the negative 2 is 1/4. If x is negative 3, 2 to the negative 3 is 1/8. So we can see these are starting to get real close to the x-axis. If I were to connect these points, graph looks like this. Okay. This is the general shape of all exponential functions. If the number 2, if the base 2 was a 3, this would just kind of grow a little bit quicker, as we'd be doing 3 to the first, 3 to the second, 3 to the third. So the points would just climb a little faster, but it still have this same kind of basic shape. Now, for this graph, its domain is negative infinity to positive infinity. As we can see, it's going left forever, and even though it's kind of shooting up, it's not straight up. It is still coming out to the right, and its range is 0 to infinity. Note the parenthesis on the 0 because it never is going to land on the x-axis. It's never actually going to hit 0. The numbers are, these fractions are just going to get closer and closer to 0, but it's never actually going to touch 0. Okay, so there's an exponential function, specifically 2 raised to the x. Okay, we can apply all the transformations that we've been doing, of course, to these exponential functions. So the directions say just describe the transformation. We're not actually going to sketch the graph. 2 raised to the x minus 1. That subtraction of 1, that minus 1, is inside the function. It's inside the function's power. And so what that does is it moves the graph, I'm going to say shifts left 1 unit. All points just moving to the left 1 unit. And actually I just got that right, or wrong. It's minus 1. We do its opposite. We all know that. Shifts to the right 1 unit. My bad. The next one, f of x is 2 raised to the negative x. The negative exponent. Now here the placement of the negative applies to which axis it's going to reflect over. This is going to reflect over the y-axis. The negative on the exponent has it reflect horizontally. Okay, we know inside the function's horizontal movement, horizontal change, so that's reflection over the y-axis. And this last one, this 3 times 2 raised to the x, the 3, since it's outside of the function, outside the x, that's a vertical stretch by a factor of 3. So all the points kind of get pulled 3 times their vertical distance as just the normal base 2 raised to the x. Alright, next I want to look at the exponential function that has base e. This is sometimes called the natural exponential function. I guess not sometimes, it is called the natural exponential function. Now, we have in a previous course in Algebra 2, we've talked about e as kind of a number and where it comes from, its numerical approximation. I may, if I have time, create a video that just shows the development of this number e, and if I do, I'll link it from this video so you can watch that if you're interested and you want to know. For the purpose of this slide, we're just going to use the approximation that e is about 2.72. E, as we know, as we're familiar with, is an irrational number, an irrational decimal that doesn't repeat, so it's just rounded to 2 decimal places. So if I were to take the exponential function f of x equals e raised to the x, and if I were to attempt to graph it over here, well, we'd begin with maybe e to the 0, and e to the 0 is 1. And then maybe e to the first, and e to the first is that decimal 2.72 raised to the first power, so that's just itself e, which is about 2.72, so that's about here. And if I wanted e to the second power, that's e squared, that's about 7. I'm just going to say it's about 7.4-ish, because on the graph we're not going to notice 4, 5, 6, 7, so it's kind of there. If I do -1, e raised to the -1 is about 0.37. So that's down here. And what we start to see is the same general shape as when we graph 2 raised to the x, just the points are in a different spot because the base is a little bit different. But the graph kind of behaves the same way. For this particular graph, its domain and range are the same as the previous one we graphed. Its domain is -infinity to +infinity, or all real numbers. Its range is 0 to infinity. If you'd like to get some more information from this graph, I'm not going to write everything down here, but you could go back into your notes and look at section 1.3 notes. This function is one of the 12 basic functions that we talked about there. So there is some more information about this particular graph there. Okay, the directions on this problem ask us to state whether the function is exponential growth or decay, and that's a new idea, we haven't talked about that yet, and describe its end behavior using limits. So first of all, just kind of what this function would look like if you need to graph it. If we need to use a graphing calculator, you can certainly do so. If I were to sketch its graph, it would look about like this. Real rough sketch. So one, is that exponential growth or is that exponential decay? Well, growth or decay kind of means just the literal sense of the word. Is the function growing from left to right, or is it decaying, which means increasing or decreasing from left to right? This shows exponential growth. Growth, as the function is increasing, it's going up from left to right. Okay. Now describe its end behavior using limits. The limits describe what's happening on the left and right side. So what's happening right here, I would say the limit as x approaches infinity of the function equals infinity. Because as we're going to the right, function's going up. So that's infinity to the right, infinity going up. And then the other end, I would describe the limit as x approaches -infinity, that means going left, of the function is 0. It is flattening out at 0. It's not going to -infinity. It will not drop below the x-axis there. Okay, another example of the same directions. State exponential growth or decay and describe its end behavior using limits. So again, if I look at a graph of this particular function. And if you're not sure what it looks like, you can easily use your graphing calculator to graph it. This one has this shape. So is this exponential growth or exponential decay? Well, the graph is from left to right, it's coming down, so I would say this is decay. And then describe its end behavior using limits. So let's see, this end, limit as x approaches infinity of f of x is 0. Going to the right, it's flattening out at 0. And this end, limit as x approaches negative infinity of f of x equals positive infinity. As we're going left, it's going up. Okay, in this example, taken out of our textbook, we're modeling population growth in a city with an exponential function. Problem says, use the data in the table, assuming the growth is exponential, when will the population of San Jose surpass 1 million people? So I've got this table of values. It's a very limited table of values. I've got year information over here and population numbers here. What I'm trying to figure out is what year will the population surpass 1 million people? And this is what I have to go on, and I know that the growth is exponential, so I'm going to use an exponential function to model this, and that's it. So let's see. Let's begin with just the exponential function. The exponential function f of x equals a times b raised to the x. And we know that the a is the initial value. So the initial value that we have in our table is the initial population value of 782,248. Okay, so that's what we have so far, just based off of that line right there. Now the model's not complete until we find the value of b. Okay, so we now need to find b. In order to find b, we're going to use this other set of information here. Now the way I use it is I'm going to substitute in for the x and the y, the other data point, this information here. So I know that the population was 895,193. When the year was 2000, I'm going to call the year 10. So what I'm doing is I'm simplifying the numbers in the table. I'm saying that 1990 is year 0, so therefore 2000 is year 10. I'm going to attempt to find what year and then translate that back into 2000 something. So I've got this equation right here. I'm trying to solve this for b. I'm going to begin by dividing by this 782,248, and yes, I'm definitely using a calculator to do that. And so I get b to the 10th equals 1.144. Now there are more decimals here, of course, and on my calculator I'm going to keep all the decimals. I'm just rounding for the sake of the work here. B is then going to be the 10th root of this decimal. So I'm going to do the 10th root of that. And so I get B to be 1.013578. I'll go maybe that far. Okay, so what does that give us then? That now makes our model, this right here, be f of x equals 782,248 times 1.013578 78 raised to the x. Okay, now I want to figure out when the population is equal to 1 million. Well, to figure out when the population is 1 million, putting 1 million into the f of x would require me to do some math that we don't really have yet. It would require me to use logarithms to solve this. So what we're going to do is a graphical approach. So let me just kind of display on paper here what I'm after, and then we'll do it all on the graphing calculator and show it that way. So let's see, we've got our function that looks kind of like this. It starts here at, right here it starts at 782,248. Of course it goes to the left also. So there's our f of x function. It is growing. What we're going to do is graph this function, and then we're also going to graph the line that's at 1 million. We're going to graph this line on our calculator, and we're going to figure out then where do these lines intersect. At what x value do those lines intersect? We're going to do all that work on the graphing calculator. So let me bring that up so we can see. So I begin by typing in the function. Okay. I'm also going to type in the other y value of 1 million. So you can see I've got them both typed in. Okay. Before I hit graph, I'm going to adjust my windows. My x values, I'm just going to go 0 to 20. So that's 0 years, which was 1990 to 20 years, just kind of guessing. And for my y values, I'm going to start at maybe 0, because that would be a population of 0. And I need to go to a population that's greater than 1 million, so I'm going to go with 1,300,000. I'm going to hit graph. So there's the first one, and yes, these are graphing kind of slow. There's the 1 million line. All we need is for them to intersect, and they do. So I'm going to calculate that intersection point way out here. Now, if I hadn't seen the intersection, I would have just made the x maximum a little bit bigger. That looks about right. So we can see the intersection point with the x value down there is what we want, 18.2. Okay, so these intersect right here and an x value of 18.2. That corresponds to this number right here. Okay, so in what year then could we say, when will the population surpass 1 million people? I would say that it was going to happen sometime in 2008. And that's probably good enough. Alright, next I want to look at a logistic growth function. It's similar to an exponential function in that it can be used to model exponential growth, maybe population growth. But whereas the exponential function growth is unrestricted, that doesn't always model real-life population growth. Very often, exponential growth functions will be bounded. For instance, a plant can only grow so tall. It can't grow forever, right? If we've got a pond and we're stocking the pond with fish, the fish cannot, the population of fish in that pond cannot grow forever. At some point, there is a cap to how much can actually grow or live in that pond. And so for that reason, we have this logistic growth function where it models the functions exponentially at the beginning, but then at some point, growth starts to taper out. Okay, so here's our kind of formal definition of this function. Okay, we let a, b, c, and k be positive constants with b such that it's less than 1, so positive number between 0 and 1 then. These two functions model this logistic growth idea of an exponential growth that levels off over time, where c, this is important, c is the limit to the growth. In other words, the population in whatever you're using to model this with will never be larger than the c. You can think of the c as the maximum possible value. Now, the graph of this particular function looks kind of like this. See if I can fit a graph down here for us. Okay, this exponential growth function will look something like this. Okay. You can see it has a domain of negative infinity to positive infinity. Its range, well, the range will always change depending on what particular what you're modeling, but you can see really that it's got kind of exponential growth right in here. It begins looking like this exponential growth curve that we've studied so far in this section, and then you can see that it starts to level off. Okay, and it starts to level off. It actually has a horizontal asymptote right here. This horizontal asymptote is the line y equals c. It's the maximum value that we can potentially grow to. So that's kind of what your logistic growth function looks like as a function. This is what its graph's going to look like. Now let's do a couple of example problems where this function is used to model real data. Okay, this example says that based on recent census data, a logistic model for the population of Dallas 2 years after 1990 is as follows. According to this model, when was the population equal to 1 million? So what we're going to do to solve this is similar to how we solved the last problem we did, where we used our graphing calculator to find an intersection point between two functions. So that's the way I'm going to go here. I'm going to begin by graphing this function. So I need to first type that in. And so it is, now this is important, the denominator needs to be put in parentheses. Okay, now the calculator uses the variable x, notice there. The problem uses the variable t. It doesn't matter what variable you're using, so in our calculator, x is t. Okay, so I've got that typed in. Now I'm going to set that equal to 1 million. Okay, I'm going to again adjust my windows. The x values are the time in years. 0 is starting at the year 1900. And so if I were to go to 100, that would be the year 2000. So let's just try that. And it looks like we're going from a population of 0 people to 1,300,000. I'm going to say that's probably fine. Let's hit graph and see what happens. So first we've got our logistic growth function. Here we can see now it's starting to level off. Are we going to get an intersection point? And we did. Okay, so I'm going to calculate that intersection point, number 5. Okay, get as close as I can. And the intersection point happens at x equals 84.5. We'll just go with that, 84.5. Okay, so in this case, t. Okay, so that's t years since 1900, so this happens in the year 19 1984. About halfway through the year 1984, the population of Dallas reached 1 million people. All right, this last example says that using 20th century U.S. Census data, the population of New York State can be modeled with this function here, where P is the population in millions, T is the number of years since 1800. So what we want to know is, what was the population of New York in 1850? Well, if T is the measure of year since 1800, then this would represent a T value of 50. And so what I need to do is substitute that T value of 50 simply into the function's T value. Because of the nature of the function and the complexity of it, that is certainly a graphing calculator type problem. So I'm going to type this in, being very careful with parentheses. So dividing, I'm going to open parentheses. Okay, that should do it. And I get 1.794. I'll show it up here. 1.794. I know what you're saying. That does not sound like the population of New York, but it says that P is the population in millions. So 1.79 means 1.79 million. So I could say that it's 1,794,000, and I could just say 558. So I've rounded that. Oops. Okay, what will the population of New York be in the year 2010? Well, 2010 is T equals 210. It's 210 years from 1800. Okay, so here's what I'm going to do. I'm going to take the expression that I had here, since I've done all the work to type it all in. I just need to edit the exponent right here to be 210 instead of 50. So according to this, it's going to be 19.16 million. Okay, so that is 19,161,673. Okay. And according to the model, what is New York's maximum sustainable population? Okay, what's the largest population New York can have? And according to this model, that is 19,875,000. Again, that's coming right there off the numerator.